Hello, good morning. Hope you're doing well today. So today we are working on lab 9, which is static equilibrium. You may have already talked about torque in the class, or maybe you haven't. For static equilibrium, we will build upon what we did in Newton's second law, where we, if an object is having zero acceleration, right? So the object could be either at rest, simply not moving at all, or moving with a constant velocity. Both of those cases, it will not have an acceleration. So if it doesn't have an acceleration, which means the force acting on the object should add up to be 0. There should be a net force of F total is 0. When it's talking about a object that we can think of as a point, we call this the point particle model. Simply balance the force is enough. But if you have a more complicated object, like a bridge, like a sign, like a poster, a poster beam, you cannot just balance all the forces, you also have to balance the torque. So you need the object to be not moving up and down or horizontally. Also, you need it to not to rotate, right? So that will be considered to be static equilibrium. So this is what we're going to explore today in this lab. Go through the definition for the torque again, because in case you haven't talked about this in class, and we did a little bit in our previous lab. So the torque is the level arm times the force. So both of those will factor in when you're trying to calculate torque. So R here is from where the center of the rotation is. You're rotating relative to which point to where the force is, right? So that's your distance R. And your force, you can see that only the perpendicular F component will generate a torque, right? So if your F is in this random direction, the horizontal component, we call it horizontal, meaning that it's in the same direction as your R. That only drags this object, try to pull it out. This force is not going to make it rotate, right? To make it rotate, you need the other component, which is perpendicular to the radius R. Okay, so we will use that force component to calculate your torque. The convention to keep torque, give it a sign, because torque is a vector. So we were saying if it causes a counterclockwise rotation, we will put a positive sign for that torque. If the torque is going to or tries to cause a clockwise rotation, we will put a negative sign for that torque. This is just a convention people follow. The unit for the torque is the unit of the force times the unit of your level arm, which is Newton times meter. Notice there's one other physics variable that has the same unit. Do you still remember which one has the same unit? Newton times meter. Which other variable also has the same unit? Anybody would like to share their thoughts? We say we apply a force for a certain amount of distance. What do we call that variable?
Is it joules?
Yeah, it is equivalent to joules when we're talking about the work the object did, right? Force times displacement is work. So that is Newton times meter. It's the same unit. Torque is actually defined to be the R cross F, okay? So when you do the calculation, this is equivalent of calculating, if you're looking at the absolute value of that, that is equivalent of using the level arm times the perpendicular component of the force. Okay, so that's why torque and work has the same unit, that's Newton times meter. But you can also say work has the unit of 1 joules because work transfer energy. But for torque, we are not going to convert this to joules. Why not? Why don't we say the unit of torque is Newton times meter, which is also how many joules? What's the difference between torque and work? You see, mathematically, work is a dot product, or we call scalar product, meaning that it gives you a scalar, it gives you a number. Work is simply just a number, it doesn't have a direction. But how about torque? Does torque have directions? Torque does have directions, it's a vector, right? So not only you have to answer how much torque, you have to say in which direction. So that for that reason, we're going to keep our units for torque Newton times meter, but we're not going to say how many joules for torque. Okay, so that's one difference between torque and work. To balance an object, right? You see this in our lives, ladders, signs, beams, buildings, bridges. So you want these objects to not only stay still, not moving, you also want it to not rotate, start. You don't want it to tilt over, right? So, which means you have to balance all the forces, and you have to balance all the torque. So all the force has to be 0, all the torque has to be 0. This is Newton's second law. You have seen this before. This is also Newton's second law. We say this is Newton's second law for rotation. You have done a lab previously on this. So if this is net force is 0, which means acceleration is 0. If net torque is 0, which means angular acceleration is 0. So you made sure not only it will not be translating, it's also not moving, rotating. It's not tilting over. So to balance an object, we need both of this to be true. So we will balance the forces. We will balance it in all different directions. X component, Y component, Z component, all have to be 0 if you have all 3 components. In terms of the torque, X and Y and Z, all the components have to be 0. So for the forces, you just add up all the forces either in the horizontal direction, to the left or to the right, or vertical direction, up or down. But for torque, you have to define relative to which rotational point. Because rotation, you can view the rotation to relative to different points. For example, I'm rotating this pencil. You can view this rotation relative to the center right here, or you can view it relative to the tip. You can look at this very differently, and you will calculate your torque differently. So we have to pick the rotation about a particular point, and that point is totally up to you, how you want to pick this point. Oftentimes we will pick it so that our calculation is easier, right? For example, if you have right here, you have a hinge and there's a force from the hinge and you don't really know what that force is. So if you pick the point rotation right at the hinge, it simplifies your calculation because right at the hinge, the force by the hinge itself is not going to give you any torque because it has no level arm, right? So that when you do the torque equations, you can ignore that force. So you pick a point that is easy for you to calculate. But essentially, you can pick any point that you want. So let's take a look at our pre-lab. Make sure we know how to set up the force and torque equations before we look at today's experiment. Here we have a seesaw, and you have two children sitting on different radius from the center, from the balancing point, the pivot point. The first children has this much mass and sit at this much distance away. The second children has this much mass and a different distance away. All right, so first question, what is the torque due to the weight of the first child about the pivot? So you can see when it's asking you about torque, it's always asking about which point. So they already picked the rotational axis for you. It's relative to this point, it's going to rotate, okay? Not relative to one end or another end. So this is the weight of the first child, and that weight is going to generate a torque. So we're going to calculate, okay, the torque due to the weight of the first child, how do we calculate it? Now in this case, the W and R are already perpendicular, right? So you simply just R1 times weight 1 is a magnitude. Well, the magnitude is easy because weight 1 is simply M1G. So you can plug in the numbers. We also need to give it a direction, right? Because torque is a vector. We found its magnitude, but what direction? It's positive if its tendency to cause a counterclockwise rotation. So take a look at this weight vector. The tendency of that torque it generated, is it going to generate a counterclockwise rotation or a clockwise rotation? Which one do you think?
Positive.
Positive. Yeah, so you're saying, Nicholas, it's going to generate or trying to generate a counterclockwise rotation, right?
Yes.
Yes, you can see that it's trying to push down, which will try to cause it to rotate counterclockwise. Very good. So this is positive, simply positive. Now the second question, B, is to calculate the other torque. Now you can see that R2 is again, and W2 are already perpendicular. So I'm simply multiplying them together is R2 and 2G. So for W2, do you think that torque would be positive or negative? This force is trying to generate a rotation in what direction? We try to push it down and causing a clockwise rotation, just the opposite of W1. So it's going to be negative because it's in the clockwise direction. That is what we, as a convention, to define that as negative. So you'll put a negative sign on that. So that's it. In order for the seesaw to not rotate, these two has to add up to be 0, right? So oftentimes you see that if your force is bigger, so if an adult is riding on the seesaw with the child, the adult, in order to, if you want to balance it, but maybe you don't want to balance it, then you'll have to sit closer to the middle. So give yourself a shorter level arm, reduce your R, so that R times the weight give you the same torque as the child. The child has a smaller weight, so they sit further and have a bigger arm, bigger level arm. So now we can balance the torque. And in order for all of this to be balanced, not only torque has to be 0, the force has to be 0 as well. So oftentimes, set up the force equation can give us some more information about calculating these different forces. What is a force pointing upward that is provided exactly by the pivot? We call this as a normal force. It's because this whole object is sitting on top of this pivot point, so it's pointing upward, supporting the entire seesaw. Seesaw itself has a negligible mass, but there are two children, so they're the weight of the children that this force is trying to balance. So if you set up your second equation for part C, you can see that, well, FP is pointing upward, right? But weight of the first child and the weight of the second child, they point downward. So if you add all the forces together, they should be 0. So you can calculate F of the P. The normal force provided by the pivot point is simply the sum of the two weights added together. So that's going to be M1 G plus M2 G. And that's it. That's how you get the force on the pivot point by looking at your force equation. Okay. So the torque equation, you can see that if we pick about the point, pivot point that it's giving, you only have to think about torque 1 and torque 2. You do not have to think about torque generated by the pivot point because there are 3 forces here, right? Weight 1, weight 2, only 2 of these forces give you torque. The pivot point FP does not give you any torque because you pick the pivot point right here at the center and the force is already at the center. It's not going to generate any torque, okay, because it has no M level arm. So that's one example of how we pick the pivot point to allow easier calculations. So you could not have to worry about this force at all when you do the torque equation. Okay. So let's go back to our lab. So we're trying to do this with using a meter stick to balance the meter stick. The first part is simply let's find the center of the mass of the meter stick, because a lot of times we are because we cannot really in this lab we cannot ignore the weight of the meter stick, and the weight is we are looking at all of the weight is acting from the center of the mass of the meter stick. Okay, so let's first find the center of the mass. They're trying to balance it, and usually it's roughly at the center. For a meter stick, it has 100 centimeters. 1 meter is 100 centimeters. So the center of the mass is around 50. In the lab, it's also pretty close. So it's up to you how you want to read this. If you're really confident, you can say, if you're not so confident, you can simply say 49 or 50 plus or minus 0.1 centimeters. That's the smallest scale. If you're really confident, you can see that the little tip might be falling within that 49.9 actually. You can say, well, I can really read into the smallest scale is 0.9.95. Now, in that case, you will just be very more confident in using half of the smallest scale. So that's also okay. This is really just depending on whoever is reading the data and how confident they feel about it. If you want to be more conservative, simply just keep it as 50 and plus or minus the smallest scale on the meter stick as your uncertainty. Okay? The mass of the meter stick, they did not measure it right away. They actually measure it later in the lab. So you just have to wait until the later parts of the lab, you can read the data. So part A is simply just getting the basic information about the meter stick. Part B and C are you're adding weights to balance it. So for part B, you're balancing 2 different masses. So viewing this meter stick as a seesaw, right? You have some mass here, some mass there. Whichever is heavier, you need to move it closer to give it a shorter level arm in order to balance it. So we are trying to set up all our force equations, and we're trying to set up all our torque equations in order to see whether they are indeed balanced. So in the lab, you will see what M1 is, how much mass they added. You will see, and then force is simply going to be that mass times 9.8 meters per second square. So that gives you the force in newtons. And this is kept at 10 centimeters. Okay. And the second force, they keep it at 70 centimeters. So this reads as 10 on the meter stick. Now this is 70 on the meter stick. The center of the mass, if you read 50, is simply just going to be 50. So you can see this weight will have a much shorter level arm than this one. So it has to be, you have to add a lot more masses in order for it to balance. We could go ahead and take a look at this particular part in our lab. Okay, so let me switch the screen share to the video and we'll take a look at the video. So they put 200 grams at the 10 meter stick. And they put, they want to see how much mass you will need in order for it to balance at the 70 centimeter mark, right? M2 actually will have a range. You can see that you have a minimum masses you can add or a maximum amount of mass you can add. Within the range, you will still consider this to be balanced. So we just need to read the minimum and maximum value to find the best value to get M2. Okay, so that's a minimum value. And that's your maximum value. Okay, so make sure that you write all of this in kilograms because you want your torque in the unit of Newton times meter later. Okay, so how do you find the best value given this range, minimum and maximum? What do we do with 395 and 402? You'll simply add them up and divide by 2, right? You'll take the average of these two values, and that's your best value. And the uncertainty for that will simply be max minus minimum divided by 2, that's your uncertainty. So for that, you can write down the force generated by weight 2 and record the corresponding distance and your corresponding level arm, and you can calculate the torque. That is for our part B. I'll switch the view to my screen share and you can take a look at how we are going to complete this table. So best value you found by looking at the average of these, right? So you'll write down here times 9.8, that's your force. Center of the mass is kept at 50 centimeters. Now, if you read it as 50, okay, you can decide however you want to read the center of mass. If you read at 50, then the distance for the first mass is how many centimeters here? So this was kept at 10. And your center of rotation is relative to this point. So this is 40 centimeters, right? So you're going to write 0.4 meters. So set for the 70 mark, that's 20 centimeters. So that's 0.2 meters. So you can calculate the torque about that particular point, about that center of mass. So this torque is going to be generated try to generate a clockwise rotation, so that's a positive torque, right? This is going to be a negative torque. These two has no torque, right? Why it has no torque? This is the weight of the meter stick and the weight of the clamp. Both of those will be measured and the mass will be given later in the video. So the meter stick has weight, the clamp has weight, but you can see that it's acting directly at the center of rotation. So it's not going to cause any angular acceleration. It will not have any torque. Likewise, the frictional force, or if you think of that as a normal force, anyway, it's the force provided by your supporting beam and the hanger to support all of the weight upward. So that force you can totally calculate because it's going to be counter balance all the weights. But that force generates no torque, 0, because that force is again acted right at the center. So that's really the first part of the experiment, is simply balancing these two masses on a meter stick where you put the center of rotation right at the center. Next part, we're trying to balance it, but we're moving it off center. So you can see we put our clamp not at 50 centimeters, now we're putting it at 30 centimeter mark. We're still going to try to balance it.
Professor?
Yes?
For the last part B, for the force for the F2, would it also be the 0.2 times 9.8?
Will be whatever the mass is times 9.8, and the mass will be the average of these two. So M2 is 0.395 plus 0.402 divided by 2.
Oh, okay.
So you have to use that mass. Thank you for asking. So part C is exactly the same as part B. The one thing that has changed is the weight of the meter stick is no longer acting at the clamp. So this is your axis of rotation. You're rotating relative to that point. But your weight is always acting through the sum of the mass of the meter stick. And you can see that if you move your axis of rotation off center, your weight of the meter stick now does provide a torque, right? So that is the only thing that's different. Everything else is the same. So to get that torque, right, you can calculate the weight of the meter stick, of course, and to calculate the level arm, you can see that this is kept as 30. Okay, this is 30 mark. This is at 50. So which means it has a level arm of 20 centimeters. So you'll write that here. And that is generating a clockwise rotation just like F2 does. So both of these has to be negative. This is negative, this is negative. The force of the clamp continued to be 0 because that's right at the axis of rotation. The frictional force, the supporting force is also 0. So you can see it's just like part B, but simply you have to consider one extra torque, and that's it. We can take a look at how they did part C in lab. Okay, so you can see now they moved the clamp to 30 centimeters. M1 is also different. M1 and M2 is still kept at 10 and 70 centimeters, but the mass is a little bit different this time. Okay, so they give you the range of the mass 2 so that you still consider the entire setup to be balanced, right? So again, do the average value of 240 and 244, you get M2, the best value. And then you can use that to calculate your torque correspondingly. So the last part is not a lab, but more of a reading off. So okay, so here they give you the mass of the ruler. In the end here, they did say something about the bridge simulation. So that's just something you don't have to measure it off the screen. You could, this has a printable version on Canvas on top of our video link. You could download that, print it out, and measure the angle. But if you really have trouble printing it, you could measure it off the screen. So we're trying to simply do this as our last part. They have a little bit different video, and that's not for your class. That's for 1210, the physics for biology. So modeling the human arm, this one you can ignore. That's not what we need. So the last part is looking at this printout and write down the forces correspondingly. Okay, so let's take a look at our printout. So how many forces are there? So in this bridge, we're trying to balance this bridge, and we have 1, 2, 3 forces we have to consider. The bridge, so the meter stick itself has a weight, so that's one of the forces. There's another hang weight, M3, that's one of the forces. F1 and 2 are actually tension, right? But the tension is everywhere the same, and it's provided through this pulley to balance these two other masses. So you can see the tension here is F1, the tension here is simply just going to be M1G. The F2 here is simply going to be M2G, okay? So we know all these forces and how much they are. You can write out the magnitude of these forces, because you can just use M times 9.8 meters per second squared. You can write out all these forces. You can write out all their positions. This is at 30, this is at 50, this is at 70, this is at 90 centimeter mark. It will take just a little bit more time effort to look at its component, okay? Because 2 of these forces are acting at an angle. So F1, for example, has an angle theta 1. You can measure that somewhere around 128 degrees. Okay, so you measure that angle. So how do you translate that into an X and Y component? Let's say we will define a direction to be, this is positive, and this is positive. Now you can define it differently. To the left is positive, or downward to be positive, that is fine. So if we define to the right is positive, how do we write down the X component of F1? So first, let's draw the vector F1 in the X direction, right? So this is F1X. The vertical one is F1Y, right? So we want to be able to write down what is F1X. You can see the angle you measure is theta 1, which means you can get this angle alpha 1 simply by alpha 1 is 180 degrees minus theta 1. So looking at this triangle, F1x is F1 times cosine of alpha 1, right? So that gives you the X component, but it's pointing to the left-hand side. So if you had defined the right-hand side to be positive, you will have to write minus negative F1 cosine alpha 1, okay? The Y component is pointing upward. The Y component is what? Is F1 sine of alpha 1. and that's upward, that's positive. So simply this one is just positive. So that's how you handle the X and Y component for F1. You do the same thing for F2, okay? F2 is a little bit simpler because theta 1 is measured directly. So F2x is simply F2 cosine theta 2. F2y is F2 sine theta 2. Okay, so that will be your 2x component. This one will be negative.
Professor?
Yeah.
I don't know if I just misunderstood what you were saying, but for theta 1, are we just going to be using the 30? Or is that a value that we're going to have to find?
Oh, theta 1, the angle, you have to use a protractor to measure the printout version, or if you measure it, off the screen. So that's an angle. The 30 is where that force is acting at, this is, if you read the scale, this is at the 30 centimeter mark. So the 30, you write down the position here.
Okay.
And
And
so
then
you measure theta, but you write down 30 as the position there.
okay.
And you have another question?
For the mass, how did you get 0.185?
That is M1.
Oh, it's given. Okay, I didn't see that. Thank you.
That's given. Okay, very good. So all of these different positions we write down because we want to figure out later in this torque calculation, what is the level arm? This is the level arm calculation, right? What is the distance to the center of the mass? So all the rotation is counted relative to the axis of rotation of here. So we view the rotation relative to that point. So relative to that point, this F1 has a 20 centimeter level arm, right? So that's 0.2 meters. F2 is from 90 to 50. That's 0.4. F3 is again from 70 to 50. Weight of the meter stick itself has 0 because you can see this force is at the center. It will give you no torque. So for the torque calculations, use the y component only because only the y component is the perpendicular one, right? And multiply that by the level arm we had just calculated right here. You have to keep track of whether that's a plus or minus, whether it's positive, counterclockwise, or negative. So F1 is going to cause a rotation in which direction? Clockwise or counterclockwise? Relative to the center. So this is the center. F1 is pointing this way. They're trying to lift it up and attempt to cause a rotation clockwise, right? So when you calculate this torque, you're going to put a negative sign here. F2 is on the other side. This will give you a counterclockwise rotation. So F2 will give you a positive torque. F3, again, is on the right-hand side, but it's downward. It's downward is going to attempt a clockwise rotation. So again, F3 will be giving you a negative torque. Okay, so you add up all the positives and the negatives, you should get 0. So the total positive and total negative should add up to be approximately 0, and positive negative force should be really close to 0. So this is for a lab to see whether the static equilibrium equations for forces and torque are satisfied. If you see a big discrepancy, like the positive forces is so much bigger than the negative, then you wanted to recheck your calculation to see if you have done it correctly. So when we have our results, we almost wanted to make sure if they're consistent. That's the last part of this lab. It's simply a bridge simulation where you read off these from the printout. Right, so that's all for today. For static equilibrium lab, do we have any questions at this point?
For part B and part C, when we're doing the torque, are we just multiplying the force times the mass?
We do the force times mass for the force, right? I'm sorry, we do the mass times 9.8 for the force. To do the torque, you will use the force times the distance, right? Is that what you were asking?
Yes.
Yeah.
And I guess like for the second one, for F2, like how would it be negative if neither one of the numbers are negative? Or do we just add the negative sign?
Oh, yes, very good point. You add the negatives. So this will give you a direction, and we will by convention say, okay, torque, which is counterclockwise, is simply a negative, which is the absolute value of R times absolute value of F. So we artificially add that negative sign onto that rotation.
Okay.
Very good question. Any other questions?
For the total positive and total negative, we just add the positives together and then add the negatives together, correct?
Yes, and again, you want to check if they cancel each other. If they add up to be zero, because the total torque should be zero for it to be balanced. And then we take the data under the condition that everything is balanced. Any other questions? Okay, if you do come up with more questions later on, feel free to email me. We will see you. I will see you guys next Monday. Okay. All right. Bye, everyone. Have a good rest of your week. Thank you. Have a good day
Take care,
yourself.
Professor.
Bye-bye. Thank you.